Hey everybody, welcome to chapter 1. We're going to have a brief discussion on section 1.3, which is about science and the scientific method. So this term science is comes from Latin, means to know. Scientists tend to be very curious in nature, and they tend to inquire about kind of phenomenon in either the physical world, the natural world, the living world. And they use a process where they make observations, hypotheses, they do experiments, and then they make conclusions from them. They tend to, they want to describe natural processes, they want to make them simpler to understand, and then be able to make predictions further upon this. And one of the ways in which they kind of do the analysis, they do this process is they record data in experiments. We have a couple different types of data. We have qualitative data, which could be descriptions, and it tends not to be numerical. And then we have it could also be like a comparison. This is bigger, this is smaller, went this way, went that way, versus quantitative data, which are in numbers. Here we have a picture of Jane Goodall studying chimpanzees. Here's a one of her what do I want to say? One of her data journal, right? And in there you can see like a lot of qualitative data. And she has a drawing of a chimpanzee. You can see like questions that she's put in there. And she's done, I would say, at least probably originally the most seminal work on chimps. So I would just say that we don't, people tend to really love quantitative data, but qualitative data is also important too. We have inductive and deductive reasoning. I'm really not going to kind of get into this, but a lot of times, like induction, we're taking like a lot of observations, and then we make specific general observations, like many of them, and we make a generalization. And then like deductive, you kind of go from small to large. So one of the important things in science is that you make observations, and then from those observations you notice patterns, you ask questions, and then from that question you're going to make a hypothesis. You think, I have this question, and then my answer to this is the hypothesis. Okay? And then your hypothesis should lead to some sort of prediction. All right, prediction about the future. And then you can take that prediction and you can design an experiment. So we have an example. It's kind of a commonplace example. Desk lamp doesn't work. Okay. Why doesn't it work? Well, it could be multiple reasons. We've got two hypotheses. Bulb is not screwed in properly. Okay. Or we got the bulb is burnt out. And you can test both of these. And you can actually come up with predictions too. So the prediction for hypothesis 1 is if we screw in the bulb properly, the desk lamp will work. The prediction for hypothesis number 2 is if we were to remove the bulb and replace it with a new one, it would work. Although that you could do that for hypothesis 1 too, also. But the idea is that, when we do a prediction, we're saying, if we change this, we expect something else to happen, or we expect something to happen, right? It's a little bit different than the hypothesis, and sometimes people get kind of hung up on it. So hypothesis one is saying the bulb's not screwed in properly. Okay, and then the prediction is if we, you could just say if we were to tighten the bulb, then it would work. Which is slightly different than the hypothesis. But we can test both of these. We have a flow chart here. You know, we've got our original observation and our question. And then, you know, hypothesis one, bulb's not in properly. We reinstall it. It'll fix the problem. We reinstall it. And hey, wait a minute, it still doesn't work. So our hypothesis isn't supported by our kind of makeshift experiment. Hypothesis two, bulb is burnt out. If we replace the bulb with a new one, it'll fix the problem. All right, so we replace it, and then the lamp works. That supports our hypothesis. I'm gonna just kind of skip over this, other than the bottom, where we don't necessarily ever prove a hypothesis in science. We can test it a bunch of different ways, but there's always a slight possibility that we could be wrong. But, you know, when you test something, you know, over years and years and years of time, and you find out that, you know, all these different types of tests that you're doing, and you're still getting kind of results that uphold your hypothesis. At a certain point, you're like, yeah, I'm really confident this is correct. And there's always a possibility that something could go wrong and change that. But, you know, at a certain point, you just feel confident that you're right. But we never prove anything in science, and that's important, especially in this day and age where I think a lot of people are like, I have scientific facts and it proves that I'm right. Well, science, we never really prove that we're right. Sometimes we just prove that we're not wrong, and that's a tough one. That would be a fruitful conversation at another point. So let's go over case study and kind of inquiry, and we've got this population of mice. The species or the genus name is Paramiscus, and this is out kind of East Coast. You've got these, and Paramiscus you can find all over the place. They seem to be found in sandy areas. So we got this mouse that lives in some white sand dunes, and then but you can find it further inland. So let's take a look. All right. Sorry, it's not on the East Coast. It's in the Gulf of Mexico. So you can see how we've got this white mouse here living in the sand dunes, and you know it's white. It's got some kind of like darker tufts of fur on its back, but it's, you know, it looks mostly kind of light color, and it looks very similar to what the sand looks like. But if you go further inland, you can kind of see this inset here where this mouse is found. You can see the habitat where it's found. There's a lot more vegetation in the inland versus the beach population. And then there's a striking difference in the fur on the back of the mouse. You know, and interestingly enough, like the fur on the bottom looks pretty much the same to me, but on the back, it's much more darker in the inland population. Okay, and this would, you know, if you were living here and you're trapping mice, and you would notice this pattern by, you know, making observations, and you might ask that question: what's driving this? What's causing the you know, kind of lighter furred mice to be out on the beach, and then the darker furred to be in the inland population? We don't really see necessarily mixing between the two, but yet they are the same species. And it probably wouldn't take too long for you to say to yourself, this is, you know, camouflage, and predators might be driving this, you know, and that's your hypothesis. So there's the beach, nice little sand dune. There's inland. You can still see sand in here, but as you're further inland, there's way more vegetation. You can start to see some trees, a lot of cover for the mouse. All right, there's a mouse. There's the inland one. The other one was the beach one. Okay, so we got two. We're matching our colors with the habitats. Our natural predators of these mice are visual hunters. So you're thinking, or I'm thinking, you've got birds, right? Hawks, falcons. Maybe you've got some foxes running around there. Probably not a lot of coyote. Maybe though, I'm not sure. But you've got a lot of these predators are going to be out kind of during the day and hunting for these mice. And you have this student scientist hypothesizing that the color patterns are adaptations to protect the mice from predators, or to basically decrease the probability of them being killed by predators. And so then Hopi Hoekstra and some students tested this hypothesis in 2010. They took models of mice that like pelts, and they painted them to match the surroundings. Okay, so you have your mice model, and you paint some white, you paint some kind of brown, and then you take equal numbers of them and you put them into each type of habitat, and then they would have looked for signs of predation. And so signs of predation would mean, it looked like did like a fox or something come along and bite this model. So at the bottom you can see the models, right? So they put these out, and I'm not sure how long they put them out for. Maybe a night, maybe a week, not sure. And they actually looked at the percentage of the models that were attacked. So we've got a beach habitat and an inland habitat. We've got, the beach habitat, you've got your white mice and then the brown mice, right? So on the beach habitat, your white mice, we would be calling like a control group, okay? So that's almost like a normal situation. We don't really expect that control group to get attacked very much. All right, it's almost like a normal situation. We expect that to be our norm, and then we're going to compare our experimental or our manipulation, which would be like the brown or the dark models of mice. Okay, and we're comparing that to our control. So we call that the non-controlled part of our experiment here, like our experimental group. So we got our control group and our experimental group. And both of these, so the experimental group is kind of like our manipulation. Like we've changed this, and we're curious to see what happens, I'm sure if that they would take like living brown mice and throw them on the sand dunes, and they'd want to see what could happen, but it's kind of hard to do because the mice they're not going to cooperate. They probably just run back to the inland because they may know that they're safer there. Who knows? So this is what we call our independent variable. We're manipulating this, we're changing it, all right, and then we're seeing like what happens, and that's our responding variable. They're looking at the number of attacks. That's our dependent variable, what we're measuring. So you can see here on the beach habitat, the light models looks like they were attacked a little bit more than 25%, and versus our experimental variable where they were almost attacked 75% of the time. Not quite. And since they used equal amounts of models, they used, I forget what it was, like, let's say 50 of the camouflaged and 50 of the non-camouflaged on the beach. Like, that's controlled. It's not like they put out 100 of the the non-camouflaged mice on the beach habitat, and only like 5. They kept those numbers even. They're keeping them the same, so we're not introducing any more variables. And we call that a control. So it's not our control variable, but it is a control in the experiment. All right. Likewise, if we go to the inland habitat, we look and you're doing the same thing. You're introducing the same numbers of mice models to see to make that comparison. In this case, in the inland habitat, now our mouse that's brown is our control variable, because that's what we normally find going on in here. And then our white mouse is our experimental variable, because that's a manipulation. We don't find those mice really on those sand dunes or in the inland area, which look a little sandy to me. And then you come back the next day, you put those models out, you come back the next day, you determine who got attacked and who didn't get attacked. And it's interesting, we see that our light models now are attacked in it's over 75% of the cases, and the dark models are attacked a little less than 25%. So those bars kind of flip. But in each case, like the camouflaged mouse was attacked around 25%, and the non-camouflage was attacked around 75%. All right, so from there they can conclude that maybe what's creating this pattern is the camouflage. All right, we got our models here. All right, so just kind of go over so we got our experimental variables. All right, we got our controls, and some of these this terminology can get kind of confusing, especially around control. So we have a controlled experiment, which means that we're keeping as many things the same as possible. All right. And we're, so for instance, like I said, like we put 50 white mice out on the sand dunes, we're putting 50 of the brown mice out, and vice versa. And we're trying to keep the inland and the beach the same. All right. You really want to try to keep, if I was doing this, I would do the inland and the beach at the same time, possibly, because you never know, like one night or one day, one night, you could have a full moon out and the other one you don't. So we're trying to keep as many variables as the same, except our experimental variables, the one that we're changing, or I like to call it a manipulation, right? With and that's where our experimental variable, we try to keep that control group, and then we have our experimental group, all right? And that's the experimental group is the change, what we manipulated, okay? So I'm going to say this. If we don't have a manipulation, we don't have an experiment. You're just collecting data otherwise. It's very important that you make a change. You see, like, okay, we have this. I'm going to see what would happen if we introduce brown mice to the sand dune, or we introduce white mice into the inland area. Okay, that's the change. That's manipulation. So independent variable is what we manipulate, and the dependent variable is what we measure. We're measuring the response. Okay, sometimes it is called a responding variable. And just want to say it's important to keep cognizant about control groups versus controls. All right, control groups, that's a part of our independent variable. Controls are just things, like I said, we're just things that we're keeping the same, so we can kind of say with confidence that what we're seeing in the data is due to our manipulation and not due to something else. So, just looking at the data on that one, I would say fairly confidently that what's driving the color patterns of those mice are it's the predators, um, and over time, we actually we see this a lot in science, right? We see that hypothesis, and over time we can kind of come up with a number of like different. We can actually, I'm sorry, we can say like with a lot of confidence that that this is something, and if people in science agree with this over time, we'll call this a theory. And I know, kind of in general, we'll talk about like, well, my theory is this. Well, a lot of times when we're just kind of talking with our friends, like, yeah, your theory is that, and like, but like if we were to look at that from a scientific kind of perspective, we would probably say, you know what, no, that's just a hypothesis, because hypotheses usually have to get tested over and over and over again in order for us to call them like a scientific theory. Okay, so you're not wrong in using this term theory if you're just kind of throwing it out with your friends, but generally in science, we don't really consider something to be a theory unless it's been tested many times and it has kind of general applicability and so forth. And in the long term, these theories can turn into like laws. And we don't really have a lot of different laws in biology because it's still kind of a new science. Physics has a number of laws, laws of thermodynamics, gravity, motion. Biology, we have some, but not a whole lot. We have a few rules. But anyway, so that's pretty much it. And I'll just leave you with this thought. It's important to know that if if you have like a hypothesis and you can't test it, it's kind of tough because science, we like to test things. We have the scientific method where I just kind of went over, where you've got your observations, your hypotheses, your predictions, your experiment, and then your conclusions, right? And if we can't test our hypothesis, we don't. It's tough, right? It could be a part of a larger body of science, but it's hard to call that like scientific, right? If we can't disprove a hypothesis, it's hard to kind of call that a scientific theory or a scientific hypothesis. If we can't run the experiment, we can't make the manipulation, and it's hard to test it. It's hard to see how that fits in science, although it could, right? And then science is kind of weird, one of these weird endeavors where the people that are participating in science are also the people that judge each other, right? So I had a friend that calls science it's a beauty contest where the contestants are also the judges. So like if you're a scientist, you're throwing, you love your hypotheses, you love your experiments, and you put it out there. Well, who are the people that judge your experiments and hypotheses and so forth? Well, it's other people that know about that, who might actually have competing hypotheses, right? So there could be a lot of times we kind of elevate science as this thing as it's objective, but there's a lot of subjectivity in there, and I'll kind of leave it at that. Thanks for watching.